So we want to talk about a constant horsepower concept today, and that is to use multiple variable displacement pumps on an engine or on a machine in order to load the engine down to a maximum constant horsepower to start with, and then we'll maybe shift whatever that constant is after that. But first things first, what I've drawn out here are two variable displacement pumps running through DCV valve banks. So there'll be separate valve banks for this. But what I have is a DCV or a variable displacement pump, a bias spring, and a stroking or servo piston over here, which will work against the bias spring always trying to upstroke, and then hydraulically we're going to try and de-stroke under the right conditions. And I have exactly the same thing over here. Another variable displacement pump, another bias spring, and another stroking piston over as such. So how this all works out is this constant horsepower is to know that really the formula for physics for input horsepower is simply flow times pressure times a constant, all divided by efficiency. And I like to look at it simply. If I want to make this input horsepower constant, whatever that constant is, then I need to know this, and I need to know this. I'm going to need to have a means to understand flow, and I'm going to have a means to monitor pressure as well, because the constant is a constant which I can never change, and the efficiency of these pumps is the efficiency of these pumps. So I'm not going to change that either. So I'm actually just going to take those out of the equation at the moment and say that's nice, but really if I want to have a constant horsepower, I need a means to monitor flow, and I need a means to monitor pressure. This is ultimately what they do. Something's got to control this servo and that servo, the stroking pistons. So say we have an engineered horsepower here of about 100 horsepower. This is what we want to pull out of it hydraulically. How do I monitor the flow out of this? Well, that's easy. First off, this is an open center system, and we can clearly see that this pump flow goes right through back to tank, other than there's a valve in the way of it. A little valve, well, really it's like a relief valve, I suppose, because it goes back to tank, but it could make a pressure here. And in fact, there's another one over here. Well, these are referred to as negative flow control valves, and the reality of it is, as soon as I move my DCV, if I was to put a pressure gauge here, if I put a pressure gauge here, I would see that there's 212 psi in order to overcome this normally closed valve. So that means there's pressure up here just sitting in neutral or neutral standby. But as soon as I move the DCV, and I'll just move it this way, as soon as I move the DCV, we should be able to see that the oil that was going to this valve is blocked. And in fact, any pressure that would have been in here is gone. It just bleeds off. And now the oil goes to an actuator out work port A and comes back from work port B to go into the tank. So whatever pressure was here is gone, which means I can use this valve. So this is my negative flow control valve, and in neutral standby we can say there's going to be, well, probably 200 psi there, and I can take that pressure and I can send it over to physically de-stroke this particular pump. So this is called negative flow control pressure, and as soon as I function the DCV, again, that pressure that was in here, for all practical purposes, the 212 that might have been in there to de-stroke that is physically drops to 0 because there's no more oil going to that, and in fact any oil that was trapped in this stroking piston is allowed to bleed off. So as soon as I move the DCV, this pump upstrokes. And that gives me a means to monitor flow, and I can feather this or do whatever I want with it, because I can have 212 psi, or I can have 100, or depending on how much oil I'm trying to push through this by how fast it's bleeding off. So I could actually vary the output of this pump, and that gives me a means to monitor flow on one pump. Well, the other side of the coin is they're actually going to be monitoring flow over on this pump as well. So now I have a means to monitor flow on both pumps. So this negative flow control is a means for me to have ultimately a way to monitor the flow on one side. And the understanding of this is like, that's good. I needed to know this. Great. I've done so. And I can play with and monitor the flow on one pump. Then I only need to know this one still. How do we monitor what kind of resistance on this pump? Because if I fully load up both pumps, I actually would probably, and I would in this system, I would stall out the engine hydraulically. And that wouldn't be ideal. We're going to build a system that is going to load down the engine to its peak torque or horsepower so that it can breathe and cool itself off. Not that it's lugging the engine, but it's running at its prime output, as efficient as possible for the horsepower we got out of it. So we want to load it down, but we don't want to overload it. So we designed this system. And right now, I've figured out a means to actually monitor the flow to this. That's good. Well, how do we get pressure? And the pressure comes from, ultimately, resistance creates pressure, ultimately, and say, by some chance, one pump is loaded and one pump isn't. Well, this is referred to as cross-sensing pressure. And cross-sensing pressure is just simply to say, yeah, there's an orifice there, and there's an orifice there, and that is to say that in between the two, every orifice creates a pressure drop for all practical purposes. We should know this by now. So in between the two, there's a different pressure here, and ultimately, there's a different pressure here. So I might say that if I was to actually have a gauge in here, the pressure might be, oh, I don't know, somewhere over here. Because ultimately this is the highest, and I get a pressure drop. And this is lower, and even this side might be trying to feed that way, but I certainly can't put a lower pressure into a higher pressure. So you could have a little bit of transfer trying to drop that way as well. I want to be clear that this is just an orifice passage. If there's oil flowing back and forth, it's only to register a pressure, and I'm going to sense that pressure right here in the middle, and I'm going to take that pressure and I'm going to do something with it. What I'm going to do with it is I'm going to hydraulically try to control these swash plate angles. So I take this down, and then I'm going to tee this off, and I'm going to go either this way with it, or I'm going to go this way with it. So here's what I got going on. In behind this particular servo, I might have a second input. And I'm going to go the other way with it. So here's what happens now. out of our first scenario, with the whole flow control, and this is to say that the higher my NFC, so I'm going to call that my negative flow control. As my negative flow control pressure went up, flow went down. Okay. And I don't need to write it out that way. I could have let it dry at first. Or I could say flow goes down. And that's exactly what happens with this. Well, this cross-sensing pressure, now this is different again. So this cross-sensing pressure, as I load up one pump, I register a pressure here. And as that pressure increases, what does it try to do to the servo cylinder? The higher the pressure here, the more it wants to de-swash this again. Take it and de-stroke that. And in fact, the cross-sensing pressure is beautiful in this way because it's finding a happy place in between the two. And it's really dictating that I know the load on this pump at any given time, and I know the load on that pump at any given time, because that will have an influence on what this is. If they're both loaded by chance, if this one's up here and this one's up here, well then this one is going to be somewhere up there as well. So they will always be talking to each other. Always be talking to each other to come up with whatever that pressure is. And that pressure is ultimately working on both swash plates, which will take, even if I load this one, this one's heavily loaded, that one, not so much. It will try and de-stroke both of those pumps. So that when we're actually running stuff, and we're usually doing, that one's kicking out, and I don't know, this one's kicking out. When these are both going to town running multiple actuators, this one's loaded and that one's not. This is allowing me to hit a maximum swash plate angle for both pumps, so that this pump might pull 75 horsepower, this one's only going to pull 25 horsepower, and our engine horsepower might be a maximum of 110. That gives us 10 horsepower below stalling it out and overloading it. Good enough. It will stay at that 10 horsepower. So 10 horsepower below whatever my engine output is. But it will always hold that constant. So if the load comes off of this one, the pressure comes off of this one, then this pressure goes down and the pump's upstroke. So the same thing happens, this negative flow control pressure, the higher that pressure, the more it wants to back out of flow. The cross-sensing pressure works exactly the same. You know what? The higher that pressure, then flow says back out of it. And if I can do that, then I can achieve a constant engineered hydraulic horsepower demand, which constant horsepower, or referred to as constant torque on the engine, to run it at its maximum efficiency all day long. And that's the start of this. There's only one other thing missing to this, and only one other thing missing to all of this. And that is to say, that's great, that's my constant horsepower, and I can achieve it. And the only thing missing is, what if you want to work in some place where, I don't know, by some chance you're in some tight quarters, you're up close to something, you're digging out a water line or some electrical line, and you don't want to go full tilt, because even if you take a load off of this machine is capable, this system is capable of a lot of flow without any resistance on it. And a lot of flow is speed. Flow is speed, so what are we going to do? We're going to build a way to turn this constant horsepower down. In other words, I'm going to shift this constant horsepower. Right now, the engineers have maxed this out. It's never going to go over, say, 100 horsepower. And that's great, but I'm going to shift it. So then we have to look at something referred to as power shift pressure. Power shift pressure is really operator input, because as far as hydraulic demand is concerned here, this thing is designed to run 100 horsepower. So if you're going to run into some situation up a building or dig out some water line, well, then you just turn the engine throttle down. Well, that means the engine isn't capable of as much horsepower anymore, but hydraulically, the only thing controlling this is that original 100 horsepower. So you can turn the engine down, but hydraulically, you're probably going to stall out the engine. And pretty sure you don't want to stall out the engine every time you put it under load. So what do we need to do? We need to shift whatever that constant horsepower is, and we'll shift it down by some chance. So here's what we do. We go, yep, we know we can have a constant. Well, that's great. Then let's shift it, and by shift it, we're going to shift it down, say, oh, I don't know, 50%. I'm going to turn my constant horsepower down 50%, knowing that I don't want all the speed and all this out of this system. So here's what we do. You know what? We need another input on here. We need a third input on this particular servo or stroking piston. In fact, we're going to need it on both sides. The question is, where does it come from now? Because I've monitored flow and I've monitored pressure on these pumps. Well, where does this come from? Well, that's not so bad actually, because really we've got another pump on here someplace potentially. Potentially we have another pump on there running some pilot controls, because for all practical purposes in today's world, we know that ultimately there's a hydraulic control running the main DCV. So even if I didn't have that, which would require pilot pressure, pilot operated DCVs, even if we don't know that, we know we've got a charge pump to protect these potentially. So what I'm saying is I have, for all practical purposes, I have right here sitting about 500 psi, which I can use as a relief valve for a pilot system. So I have about 500 psi there. That's good. So if I was going to, oh, I don't know, throw an operator in here and have the operator control this valve, so the operator can physically control that valve, which ultimately can send so a normally open valve, a pressure reducing valve for all practical purposes, that the operator becomes a spring tension. Pressure regulated feedback as well. So, but let's just keep it a pressure reducing valve. And I would be able to control this pressure downstream of this valve, because this valve actually senses downstream of the valve to physically control it. So if I sense downstream, then I can control this pressure. And if I can control that pressure by controlling the spring force, then I can either have this go up or down. And that is to say that I could have potentially 0 here, or I could have potentially all the way up to even 500 psi downstream of this valve, all with operator control. So we steal oil out of the pilot system, which is the control side of it, and we control whatever that constant horsepower is. And by controlling it, we'll just throw some pressure at this. And if I throw some pressure at it, that would try and de-stroke this. And now instead of 20 degrees max, nope. Now I can only get maybe 10 degrees maximum on this particular pump. And by the way, because you're going to try and control the maximum horsepower, what we're going to do is we're going to send it all the way over and control both pumps to physically now only produce 10 degrees. You wanted to turn this constant horsepower down 50%? No problem. The operator has a little dial in the cab and he hydraulically adjusts the dial, and what he doesn't realize is you're using this lovely pilot system to, which is really the control for the main pumps. Well, let's use that control, and we're now going to have something called power shift pressure. So this is power shift pressure, which no longer is pilot, it's infinitely variable. Could be 0, which means, hey, pumps go to town, they produce, or it's right up to that 100 horsepower, whatever the maximum engineered is. Or he can actually, the operator can say, hey, I want to turn down the constant horsepower, so I want to slow this machine down. And so now the pumps are only capable of a maximum swash plate angle of 10. And it'll run at that maximum swash plate angle of 10. And the cross-sensing pressure will vary it infinitely from minimal maximum 10 degrees, because the power shift pressure is limiting whatever the constant will be. And I just want to be clear on that it is operator input. And the beautiful thing about this operator input is that, well, if we know you're only going to use 50% of its hydraulic capabilities, then why wouldn't we turn that and connect that to the engine control? And so now we can turn down the engine speed finally. So we don't start by turning down the engine speed, we finish by turning down the engine speed. Hydraulically, we had to control it first. First and foremost, we had to turn down whatever that constant hydraulic demand was going to be, and that's power shift pressure. So again, the power shift pressure, if it's high, then really flow goes down, because all three of them are working exactly the same, like trying to de-stroke that bias spring. That's the reality of it. Ultimately, this constant horsepower system is really about using all the engine's capabilities all the time. It's a very efficient system, and that is to say, when there's no real load on the actuators, these pumps pick up and they upstroke, and the actuator actually speeds up. So this is about production, 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 and yet you still want to be able to physically lift something and generate enough force on that, and there's a lot of pressure on it. Okay, well, you know what? Then the pumps gotta back out of it. They gotta de-stroke, or will hydraulically overload the engine. Fine, just back off in the flow, and you'll slow down, but you'll still be able to lift whatever it is you're trying to lift. That's the simpler side of that. And again, the only other final piece to this puzzle is the power shift pressure, which takes whatever that engineered constant was and allows the operator to shift that constant down, usually.